Okay, let's start. So conceptually in this talk, you're not going to learn anything new. However, when I was planning the lectures, I expected like half of you people to be CMS because India is CMS. And there's a network called particle net, which is essentially dynamic edge convolution, the core principle, which is very popular in CMS, and I see most of the results quoting that particle net efficiency, etc., is doing wonder. Okay, so I thought since I'm giving a tutorial, come few lectures on graph networks, why don't we do an exercise where we will try to understand what's the core concept and try to build the network from scratch and try to see how to do some machine learning with it. But I don't know if you have done the previous exercises or not, it's up to you. But in case those of you are in CMS and want to do, I don't know, in CMS Higgs to BB bar, HGCal, everything uses particle net. I mean, from what I have heard from my friends and everyone. So yeah, if you know what's going on, it's easier to try those techniques. Okay, so that's the point of this talk. However, I don't have a pointer. Yeah, great. So the real paper which started discussing this method is actually a computer science paper in early 2018. What they tried to do is that they were looking onto shape classification problem. So there is some data set called ModelNet 40. What it does, each element of that data is some shape, a table, car, guitar. I mean, there are aeroplanes and things like that. And by now, probably you can understand that if you have finite number of points sample from any geometrical object, that is a point cloud structure, a set. And given that set structure, is there a way that you will operate a neural network function and it will tell you what kind of object it is? And the more different the classes increase, it's become more and more complex. So this is a good playground for all set learning problem that can a set-based function improve the classification efficiency or segmentation efficiency for a point cloud structure like this. And there, Michael Braunstein and his collaborators proposed this idea called dynamic graph convolutional network. So what it is? Let's try to understand in principle. If you're given a point cloud like this, you can form a graph, be it nearest neighbor adjacency matrix, be it k nearest neighbor adjacency matrix, a radius graph, all the kind of graph you can make. By the way, k nearest neighbor we have already discussed. Who is not familiar with radius graph? Good. So if you it's even simpler. Like you have a point cloud, you have a target node, you ask, given a fixed distance from the node, whichever point is falling within a higher dimensional circle, or if it's 3-dimensional, it's a sphere, then whichever nodes fall into this volume, you will all establish an edge with it. This is called spherical graph. Okay. So they figured out that if this graph construction can be done in a learned space, then it might happen that in a regular 3D coordinates, whichever points are farther, here the blue, it's given a target point, which is marked by red. The blue points are farther, the yellowish points are closer to the target point. Now, is it possible that you write down the coordinates of the same points in some learned space where the farther points become closer to this point and the further point starts exchanging messages with the target point? This is the core principle they asked. And that led them to define dynamic graph construction. What is dynamic about dynamic graph construction? So first, we are now all familiar with message passing neural networks. So given a target node, you aggregate the messages and update the features sitting on the node. And this x prime is a function of the original x and the neural network parameters, right? Now, if you take x prime as the new coordinates and build a k nearest neighbor or fixed radius graph, then certainly the adjacency matrix is bound to change, because earlier the k nearest neighbors were computed based on x coordinates. And if you recompute the k nearest neighborhood based on x prime coordinates, then surely x prime is a completely new data compared to x, and hence the adjacency matrix is supposed to change. So it might happen that in a graph like this, if the farthest points were not connected to the target point, in this x prime coordinates, it might happen those farther points are now connected to a target point. And on the second iteration of message passing, you can probably exchange information with a farther point to the nearby point. So are there any advantage of this? That's what they tried to see, and if they can improve the classification performance. So this is the 2018 story. Okay. So here what the concept goes, that initially you had x data, you had some graph. Now this x points undergoes some processing through h of theta, which is a neural network layer. And this gray points are the latent space representation of these points. And you build a new edge out of this latent representation. And you, as you keep changing the latent representation of the node data, you rebuild the graph each time and do message passing. Okay, so earlier, once the graph was defined, the topology of the graph was fixed. Static graph. You have a graph, you have nodes, you have a fixed adjacency matrix, and you do message passing operation. Here, given the current node features, you rebuild the graph and then do the message passing. That's the only difference. That's the core concept of dynamic graph. The dynamic about dynamic graph is that each time you rebuild the adjacency matrix. Yes? In that original dataset which they used. Stick to one algorithm, k nearest neighbor, but k nearest neighbor on a new set of data, because the node features have been updated. Okay, and once you rebuild k nearest neighbor on the updated features, the adjacency matrix coming out of the repeated algorithm is different from what you started with, right? Jet data. Right? Exactly. It won't be same parameters. In fact, if you're starting with a eta phi plane 2 dimensions, the dimension of the feature space can be 30 dimensional, depending. And now you compute Euclidean distances in that 30 dimensional space. you have a coordinate of the points. Okay, so point A in D dimension has numbers like, say, XA, let's D, and this is for point A. For point B, D dimension. So now the Euclidean distance should be like XA minus XB for the point I square summed over I. Right. The fact that you're computing Euclidean distance, you're just, instead of three-dimensional vectors, you're doing higher dimensional vector. And as you increase the number of dimension, each dimension will contribute a square sum here in the Euclidean distance. So irrespective of the dimension, the definition doesn't change. No, we are always mapping RD to RD prime kind of thing, right? I mean, if it's a Boolean, how do you represent them as a point cloud? So, sorry? Well, but you will essentially treat it as 1-0 kind of thing, which will again map to some continuous number in the next iteration. Yeah. Okay. So it's the concept of dynamic graph construction, dynamic adjacency matrix construction is clear. I hope so. Number of vertices are not changing. But it might happen that in the feature space, when you recompute the adjacency matrix, some of the node can be an isolated node and things like that. But the number of points which you started with are all returned. Right? Okay, great. Oops. Oh, okay. So now, these people in 2018 did the simultaneous classification and segmentation of the point cloud. Classification, you understood that whether that object is a chair or a car, what's the property of the object. Now, segmentation is that given a point cloud, why it's not changing here? You could have asked which part is the arm of the guitar and which part is the base of the guitar. Can a neural network identify, can it do a segmentation? Like when you see scenes like the boxes are drawn dynamically in some driving scenes, etc. That's a segmentation task, scene segmentation task. Similarly, you can ask whether it's a point cloud segmentation task, like top of a table versus legs of a table. Which part is what? So they simultaneously solved this problem, and that's the model they built. So keep an eye on the model that there is one part which is doing the classification and one part which is doing the segmentation, and they are all starting from a transformed representation which is non-learned. So they just pre-processed the point cloud and then had two different blocks altogether which didn't share any weight, and solve the problem simultaneously. Okay. However, there is an interesting concept of skip connection. What does that mean? That if you get an output, you're appending the input to the output of the network. How many of you have done some training on ResNet while doing CNN families? One, only one. So what was the difference between an AlexNet and a ResNet? Residual connection. What was the input? You append it with the output. You're doing exactly the same thing here. You get an output, you just merge the input to the output. And the same concept we will see for particle net as well. You define, but the information is loaded on top of the output. Okay, if they have exactly the same dimensions, you can directly do an algebraic sum. If there is not, then you concat according to the featured dimension. Okay. So now comes the particle net paper, Locos, Goskos, and Huelen-Koo. They applied the same, exactly same concept on top quark jets. So we have large radii jet for boosted particles. Jets are point cloud. By now, I tried to bang this concept 100 times in your head. And they took the point cloud and exactly tried to implement the same idea. So the HConf block, which they formed in their paper, this was the one. What is that? Each point cloud has a coordinate and features, right? So going back to the jet example, each particle had an eta phi, and then there are kinematic properties of the particle, PT, and other stuff, which are features. From the coordinate, they computed the adjacency matrix using the KNN algorithm, formulated the adjacency matrix, and using this multi-layer perceptron, they did the message passing, finally did an aggregation, and after the aggregation, they use the input to the output they added. Exactly the same concept what was used for the DGCNN original paper. And after passing it through a ReLU, you have updated node representation, node features. So it tries to retain the differentiating features of the input data. Okay, so first it was used in ResNet, and then there is something called UNet. Have you experienced UNet? UNet is something like in the image where you solve a per pixel kind of problem, you have CNN layers, convolutional layers. Each time you apply a convolutional layer to the image size shrinks because you have a finite kernel size. And once the image shrinks, then you apply a method called transposed convolution, which expands the size of the image. So it goes up, and the way it has been designed so that at a particular iteration, the size of the input flow image and outgoing image are similar. So you just add this to data. This is called skip connection. And this method, and because of this shape, that the data size shrinking down and going up, it's called UNet. Okay. So, and for ResNet, it was forward passing the input data. All these two methods retain the original differentiability structure which was present in the original data. I mean, not everything got swamped away by the latent space representation. Okay. So this stuff, and now what did they do? So in the original particle net, once they have output of an H convolutional block, so this arrow should be compared to here. They just copied the information, and hence the output, the new latent space output, is going as the new set of coordinates and the new set of features. And once you have a new set of learned coordinate representation, if you construct a KNN with learned representation, you will get a new adjacency matrix. And after each layer, if you keep stacking the blocks of H convolution one after another, each time you pass it through, you have a new graph structure. So this is how the dynamic graphs are constructed repetitively after each forward passing through an H convolution. And again, you do a message passing. Right? Fine. And then finally, you decide after a few iterations of message passing, what do you want to do with that updated graph structure? You can use it for classification, you can do for node segmentation, whatever you want. That's either a graph level task, a node level task, or an edge level task. But conceptually, what's happening should be clear in your mind. Right? Okay. Now let's go to some coding, how to implement it. Are there any questions on at the conceptual level what we discussed? Good. Okay, so we have the same bunch of imports and the same data set as yesterday. Haven't I? If not, let me do it live. You have it. Okay, good. So download it and then we should start. Right, so until this point, it's something similar to what we were doing yesterday. We have the same JET data set. We have a block for building multi-layer perceptron and things are like that. Now, what is an H convolution operation? Any function, if the message network is just a network which takes the node features, that is called like an H convolution, and the original DGCNN paper proposed this one. So you see there is a kind of asymmetric function. One is xi, another is xj minus xi, and you apply two different pieces of multi-layered perceptron on them to create the edge data. Right? So you know now the message function which creates the message. It will have two pieces of neural network and create Mij. So let's code this up. Let's just have this formula in mind and let's code this up. So this is something like an edge convolution. So can you relate the formula and the code of your own now? Because there are quite few occasions where we try to associate a mathematical formula with a piece of code. Is it clear that theta m is same as this and phi, and if requires you apply an activation here? Right? Good. Now let's convert this H convolution to dynamic H convolution. What changes? Can you tell me what exactly changed and where? So you see here, it's taking only X, the features as input. On the fly, it's building a KNN graph from X. and then doing the propagate, the message passing operation using this on the fly created adjacency matrix. Right? Good. Now the current CMS model, they have a very nice web page I found. They created this very complicated picture. I got confused, but ultimately it's simple. They have the implementation in this XAI for HEP where they created some feature propagation, layer-wise feature propagation kind of interpretability. But anyway, what's the core thing happening? The basic hconf block, you have the features, you have a multi-layer perceptron with several parameters, and you do an aggregation over the k nearest neighbor, where you have formed a k nearest neighbor adjacency on the fly. Once you have the input features and coordinates, you pass to the edge convolution block, which is this whole thing. It gives one output. The one output is repeated to the second block as an input, and it also goes as the coordinate. Same goes on, and output of each of these block is stored later to be concatenated into one big tensor. Right? So if you have 3 edge convolutional block, then you have 3 different node features as output. Each time a message passing is happening on a different adjacency structure, you take the output and club them together into one big vector. And finally, you can apply some global pooling according to the kind of task you want to do. But the updated structure happens here, and the rest of the stuff undergoes a global pooling. So now here is one big tensor for the whole graph, is the global data, and you apply another piece of multi-layer perceptron, which is like a fully connected object, and you give an output. It can, if you want to do classification, whether it's a Higgs jet versus top jet, you do classify on this course, you can try to regress mass. We will see some performance plots there. Sorry? Oh, hconf means, you remember, we will show you the network itself, which is that theta and phi. That is like an MLP. And you need to say how many linear and nonlinear you stack to build one MLP. And that's the number you specify by this list. That's what they used. Yeah. No. 16 means the k nearest neighbor was used k equal to 16. Okay. So let's build it. So we have a simple implementation of a hconf network. And the way it's done, that this is a message passing network where you will create the messages. This is now you're very familiar with. But what will be the multi-layer perceptron which will be used as edge network, that is callable. So here you see that when we define the network, this is a callable neural network NN library object. So you can pass your favorite piece of MLP here, and if the feed forward operation is okay, then there is a whole lot of flexibility what kind of network you're going to use here. The MLP can be stack of linear and ReLU, that can be in convolution 1D and ReLU. All pieces are allowable here. And then you use that to create the message function. Okay. The pair tensor, you remember, one hconf block gives output one number. Let's go back to the picture. both here and in the slides as well. Let's stick to here. One hconf block creates actually one vector kind of thing. Okay, yeah. And that is used for both adjacency matrix construction as well as that's the starting feature of the nodes for the next layer. So you just replicate the same output x as a pair x comma x for the next layer. One piece is used as a node feature, other piece is used for the adjacency matrix creation. So this double arrowing thing, one black, one red, is just that pair tensor. That there is only one output that has been just made a twin. Okay. Right. And now, given that the hconf block was so defined that any MLP will do, we have just built our own MLP on fly. You can build anything you like to do here and pass it to make the actual message passing happen. Okay, very good. A question for you. A message passing network, at which function it does the message passing operation? No, there's a keyword for that, propagate, right? When you call the propagate, three consecutive functions, that H function, aggregation, and node update functions are called simultaneously. Here, there is no propagate. What happened here? Correct. So that function has been used here because this is just an derived from the previous one. So the propagate is defined when you call a constructor of hconf LRP. And whatever propagate rule you define there, that will be executed here. Is this clear? Good. Now the full particle net. Okay. Essentially, you have some keyword arguments that what you want to do, whether it's a classification, what kind of, how many number of H convolution layers, etc. you want to stack into. All this should be passed here. The kernel sizes. The question you were asking that what was the first number and what were the other numbers, those are all given here. Okay. And once you do it, the core important part is here. See, we create the module list, the hconf blocks. And once you look into the forward function, it's happening over a loop. So for all H convolution blocks, there is a new activation, and then the X has been rewritten. Okay. And at this step, that concatenation, that the output of the previous has been appended with the output of the next, the feed forward arrows which were shown. That is happening at this step. Okay. So the picture we had seen that this concatenation is happening one after another, that is happening through this torch.cat block. And the rest, according to what you want, you can just return updated node features and the scores, or you want to return that what are the new set of adjacency metrics that should be created. Also, you can put that information in the storage, because later sometime you want to visualize that we are talking about dynamic edge construction, how it's happening actually. After each block of message passing operation, how it's actually getting updated. This is a nice thing to visualize. So I will let you do that because all the necessary codes are there. Okay. So now let's see with the same data loader and the data structure. Again, we make a batched graph. Our batch graph have everything, and we created the model. Okay. And we do a forward passing. See, it's everything runs smooth with right kind of gradient function. So, and once you can pass the graph through the full network, then you can pick up which information of the output you want to use for computing loss functions, depending on the kind of task you want to do, and do a proper training. So the training blocks which we provided in the first set of lectures where we were doing the deep sets and in the first lectures, they will exactly work on the outputs of this out of the box. Now, as a part of exercise, if you want to do, remember when we first introduced graphs, we said like given a graph, how to see its adjacency matrix and things like that. You already have the code snippets for those kind of things. You also know how to store the updated edge representation because that's what exactly is returned. I will request you to use that piece of code and pass these outputs just to visualize how the adjacency matrix is evolving after each layer of edge convolution. I mean, here I didn't do the full training, but you have the materials. If you do a full training, at least give 15, 20 epochs, see if the loss curve is decreasing, then it should be learning something. You needn't get a full optimized performance. But after 10, 15 epochs, the model state you get, try to visualize the evolution of the graph after each message passing layer. That will be an interesting visualization for you to understand that as the training goes on, which set of edges are getting connected, and that will give you a notion of interpretability, that if you're trying to tag a top jet, a Higgs jet, which substructured particle are getting connected, because that's the connection is also learned. Okay, so if you try to do that, then on the last day we can try some interpretability of this kind of networks. But for that, I need you to do a little work and try to see yourself that indeed, out of all these codes, you can see an evolving edge structure on the graphs. Right? Any question? So I don't have much else for today. I just wanted to use this as a example because this is so popular. So I thought, why don't we just discuss it in details and exactly show you how to build a particle net starting from zero, what are the ingredients going into, and at which stage the dynamical graph construction is happening. What does it mean to have a dynamic graph? All this stuff. And once you go back to your institute, you can compare the performances of a graph net versus a particle net. I mean, they shouldn't be different, they should be similar. But you have now the whole general concept of edge update, node update, global update versus dynamic edge convolution. If you want to play with them, just play with them and compare the performance on your favorite task. When you will write a paper, maybe next month, maybe next year, whenever, you can try to think which is working better and why. Okay. So if you try out the edge visualization and you show me that how it's changing, then we can discuss a little interpretability stuff as well. Okay. I don't have anything much for the day, so I will.
I guess we can try it right here.
Right,
Yeah.
you try it. I mean, we have time.
We have time, so we'll try it here. We're running this and this displaying this data we already have downloaded or shared.
Yeah, data everyone should have. All the data loader is there. Sure. Yeah. The color coding was the nearby points are yellowish and the far by points were blue. In the geometrical space, like what the network is interpreting, that for the well classified cases, it really tries to learn the distance in a dynamic way, and the network could predict that, okay, these are the points even in the for a well classified spaces. These were the nearest points which were used for my optimal score prediction, versus these points were interpreted as farther points for my score predictions. The red dot, yes, yes. For a so this is like in a point cloud, they were trying to interpret, given a target node, which information was used, and that's how they build the color coding. No, always remember that the nodes, they live in a feature space, right? And in that feature space, you can define your metric to compute the distance between a pair of nodes. So that's the distance we are talking about. Jet case. Right. In this 16-dimensional space. Exactly. Now, it's a tricky question. How do you define the metric in that 16-dimensional space? But people don't go into complexity and take Euclidean distance by default. Right? Eta phi starting. Yes, because the output of the first layer is replicated. You know, that diagram, you make a pair, and this updated latent space features are now used to compute the distance between all the nodes to create a new set of adjacency matrix. Right. That goes as a feature itself. Yeah, of course. So all the information which were accessible all get updated. Now your particle lives in a completely new learned feature space. Right? So since we finished like half an hour early, just give it a try. And